So in this lecture, we will study the time varying potential, and we know that there are two type of potential. One is called the electric potential V, and which is a scalar quantity, and another term is a vector magnetic potential, which is a vector. It is given in the name. For the static fields, if the fields are static, these potentials are given by these two expressions. One is for the electric potential V, which is given here, and another is for the vector magnetic potential, which is given here. And these two equations are for static fields. Now, in this lecture, we will see what are the expressions of these potentials when the fields are time varying. So let's start with this uh, Maxwell's equation that we know that for the time varying fields, curl of E is not equals to 0. Rather, it is equals to minus del B over del T. Also, we have seen that E can be written in terms of the gradient of V. So E is equals to minus gradient of V here. Now, if we take the curl of E, then it will be curl of E equals to curl into minus the gradient of V. Now we already know that gradient curl of gradient is always 0. So this will lead to 0. So it means that curl of E is coming out to be 0. Whereas for the time varying fields, this is not equals to 0. So it contradicts these two equations. Therefore, will not only be equals to minus gradient of V, but rather some more expression will be there, so that when it becomes 0, some additional term should be there. Here some additional term should come, so that here it should not become 0. So this is a basic formulation. That's for time varying field. We have to add something here. Some more thing will come here for the electric fields. Okay, so it is written here that E equals to minus gradient of V is not a valid when a time varying magnetic field is present. Therefore, new approach to potential is required. So in this case, we cannot if you know the E, we can't compute the V from this formula, but rather we have to see in a different way. So what we are going to do, we will obtain a differential equation for V and A. We will obtain the differential equation of V. Similarly, we will obtain the differential equation of A. And the solution of that differential equation will give the expression or equation of V for the time varying fields. So basically starting of this is the Maxwell's equation again. We start with the divergence of B equals to 0. And when divergence of B equals to 0, it means we can put B as the curl of some vector quantity. So when B equals to curl of vector quantity, then the divergence of curl of any vector is 0. So then we define here the vector magnetic potential. Now again, taking del cross E minus del V over del T, this is coming from the Maxwell's equation, and replacing B from here, and this will leads to this expression. So we can go on driving this expression. You can see later on how these are the steps. So you go through these steps. So finally what we achieve when we rewrite these equations and replace one equation and another and apply some theorems and identities, so we will reach at this point. So I am skipping all these derivations, you can see yourself. So finally what we get two differential equations. One differential equations in V, another differential equation in A. So here this differential equation have some special coordinates. This is del square V. So this factor is a derivative of a special coordinate, and here you have the T. The solution of V will depend upon, the solution will comes out to be depending upon the spatial coordinate and as well as the time coordinate. So this potential will be a function of x, y, z as well as with the t. So it will also be a time varying field solution. Similarly, this A also be a, when the solution, we will obtain a solution of this differential equations. So we will get the A as a function of x, y, z and time as well. So these are the time varying potentials now. With time varying time, this potential may vary. So these are the solutions will give us the expressions, and especially these two equations are called the wave equations. So why they are called the wave equations? Because in their solution, when we see in the future lectures, that the solution of these two equations, the equation just comes out to be such a way that they will appear to be a moving wave. They will call to be a wave, that somehow the wave is seems to be a wave. When we visualize these expression, we will see that it seems to be a some sort of moving waves. So these equations are called the wave equations. So I've written the solution here. That solution of these first wave equation is equals to v equals to integral of rho v dv over 4 pi epsilon r over whole volume v. V for this, if we have the volume charge density, then we have to integrate whole volume to get a total charge. Similarly, for the vector potential, these are the expressions. Now here the difference between the static and the magnetic fields are two. First one is that rho v is a function of spatial coordinate as well as the time coordinate. So rho v is a function of x, y, z, and t. Here. Similarly, j is a function of x, y, and z. This is also a j is a function of all four coordinates. So this is a function of the spatial coordinate as well as the time coordinate. Secondly, we have the square brackets. The square brackets are explained as follows. The where term rho v or this square j means that the time t in rho v xyz t, or here this j xyz t is replaced by the retarded time t dash given by t dash equals to t minus rv. What it means that where v is the speed which depend upon the medium is given by this here. What it means then, let me explain it here. If you have some charge at this point, this is let rho v, and we are observing the potential at distance r. Let this the distance r, and we are obtain this at this point we are watching the potential v. Now, if rho v is constant and r is constant, because spatial coordinates are constant here we are observing, then this v will become comes out to be some value and it will be constant. Now is as rho v will change with time, is a function of time because we are observing the time varying fields. So if electric and magnetic fields are changing with time, so also the charge may vary with time also. So if this rho v is changing with time, so its effects over in potential will not come instantly, but rather it will be effect will come later after certain time, and this time is called the tau. The effect of will be seen here after certain time. You will not get directly as we change rho v here, and at the same moment you will get the variation in the v, but this effect will propagate from here to here, and it will take certain time tau. Now this time tau will depend upon how to find this tau. We know the distance is r, so r divided by the speed of the propagation of the effect, and this will be depending upon the medium, and let we call this is speed to be v, and v is equals to the 1 over under root mu epsilon. You will see it later also. So it will, if you have some speed v, then this time tau is equals to r over v. So if you change rho v here at time t, then this v will change due to the change in rho v after certain time. It will not change at the same moment, but rather it will take certain time, and it will be delayed by this effect r over v. So it seems that what you have, that this v here, v and a, that when you observe the v, that be delayed by t minus r over v. T is the time at which j is changing, and its effect will be delayed, and it will be delayed by r over v. So where r is the distance between the source point and observation point, and v is given over here. Now the potential v and a given by 8 and 9 here are called the retarded electric scalar potential and retarded magnetic vector potential, because they will be retarded in the time. After some certain time they will appear. So what you can include that the scalar or vector potential at any point is not due to the magnitude of the charge density or current density at some distinct point at the same instant, but it is due to the magnitude of the source at some previous time. So what is happening in the previous time, that effect will come right now. Now if the sum is changing right now, its effects come in the later stages. So it will have some delay, and this delay will depend upon how far you are observing. If you are observing near here, it will have a very small difference. Instantly it will change. If you have a here, it will be changed later. So it will take certain time. If you are far away, then it will be take a much time to come that effect. That's mean here that T minus R over V. Okay, so this is a time varying potential we obtain when the fields are changing. Okay, so here we stop, and then next is the time harmonic fields, and this time harmonic fields are very important. These are the basis for the wave equations, and generally we have to focus for the transmission, and for the wave transmission we have to understand the wave phenomena. So this is the starting point from the wave equations. To understand the wave equations, we have to understand the phasor forms and what do you mean by the harmonic field and so on. The next topic will be the sinusoidal variation of fields or the time harmonic fields.